Methanol, CH3OH, can be made industrially by the reaction of carbon monoxide with hydrogen as shown in equilibrium 1. Part A. Predict the conditions of pressure and temperature that would give the maximum equilibrium yield of methanol in equilibrium 1. Explain your answer. So firstly, we want to be producing more methanol to get a maximum equilibrium yield. So we want to favour the right-hand side of this reaction, or this equilibrium. The right-hand side has fewer gaseous moles, so in order to push it and favour the right-hand side, we need to have a high pressure. The forwards reaction is exothermic, and to favour the forwards reaction, we need a low temperature. So to get the 3 marks for this question, you get a mark in this question for saying that the right-hand side has fewer gaseous moles. You get a mark for saying that the forwards reaction is exothermic, and then you get a mark for saying high pressure, low temperature. Part B. A catalyst is used in the production of methanol in equilibrium 1. State 2 ways that the use of catalysts helps chemical companies to make their processes more sustainable and less harmful to the environment. So the first way that catalysts mean that the process is more sustainable and less harmful to the environment is that they result in a lower energy demand. And the second way is that you've got less carbon dioxide emissions or less fossil fuel emissions. So these are the 2 points to get the 2 marks in this question. Part C. Standard entropy values are given below. A chemist proposed producing methanol at 525 Kelvin using equilibrium 1. Explain with a calculation whether the production of methanol is feasible at 525 Kelvin. So the first thing we need to do is work out delta S. So that's going to be the product of the equilibrium minus the reactants. So that's 238 minus 198 plus 2 times 131. Because if we look at equilibrium 1, that would be CO plus 2H2 equilibrium CH3OH. So we can see how we've multiplied by 2 because we've got these 2 hydrogens. So delta S is going to be equal to minus 222 joules per Kelvin per mole. But as standard, we usually go with kilojoules. So that's going to be minus 0.222 kilojoules per mole per Kelvin. So now we're going to use an equation, and that equation is delta G equals delta H minus T delta S. So plugging in the numbers to work out delta G, that's going to be minus 91, because that's what we're told in the question, minus 525 multiplied by minus 0.222, which equals 25.55 kilojoules per mole. So looking at where these numbers come from, this minus 91 is the delta H value for equilibrium 1, and it equals minus 91 kilojoules per mole. So that's why it's better to convert joules into kilojoules, because then you are changing less things that you're given in the question. And then you're minusing your temperature, which is told in the question is 525 Kelvin, and then you're multiplying by your delta S that you've just calculated in order to get this final answer of 25.55 kilojoules per mole. Now we need to talk about whether the reaction is feasible or not, and this reaction is not feasible. So the reason for this is because the Gibbs free energy, or delta G, is bigger than 0, so it's a very positive number, which means it's not feasible. To get the 5 marks for this question, you get a mark for using the delta S equation, you get a mark for calculating minus 222 or minus 0.222. You get a mark for using the delta G equation. You get a mark for calculating 25.55, and then you get a mark for saying not feasible because delta G is bigger than 0. Part D. At 298 Kelvin, the free energy change delta G for the production of methanol in equilibrium 1 is minus 2.48 times 10 to the 4 joules per mole. Delta G is linked to Kp by the relationship delta G equals minus RT ln Kp, where R is the gas constant and T is temperature in Kelvin. Calculate Kp for equilibrium 1 at 298 Kelvin and give your answer to 3 significant figures. The first thing we're going to do in this question is highlight the important bits of information. So firstly, the temperature we're given, the joules per mole or the delta G value, then that we have this equation, what each one stands for in the equation, so R is gas constant and T is temperature, and we need to calculate Kp for equilibrium 1 to 3 significant figures. So the first thing we're going to do in this question is rearrange the equation that we're given for ln Kp. So that's going to be ln Kp is equal to delta G divided by minus RT. So then we can plug in the numbers. So we can do 2.48 times 10 to the 4, and that's from this delta G value we're given in the question. Then divided by negative 8.314 multiplied by 298, which equals 10.01. And that's ln Kp. But we don't want ln Kp, we want Kp on its own. So to work out Kp, we need to do e to the 10.01, which equals 2.22 times 10 to the 4. Now we need to work out units, because there's a space in the question for units. And this is our answer to 3 significant figures. So that's good, we've answered that bit. But in terms of units, if we were to write an expression for Kp, that's going to be Kp is equal to the partial pressure of methanol, so CH3OH, divided by the partial pressure of carbon monoxide times the partial pressure of hydrogen squared. And that's taken from equilibrium 1. So if we write that out again, that's going to be carbon monoxide plus 2 hydrogens equilibrium to methanol. So we can see where the 2 is coming from, that's being the squared in this Kp. Then if we say that each one is measured in atmospheres, so that's going to be an atmosphere on the top, atmosphere on the bottom times atmosphere squared. We can cancel out these 2, so we're left with atmospheres to the minus 2 as our units, which we then write on the line, so ATM to the minus 2, and then 2.22 times 10 to the 4. To get the 3 marks for this question, you get a mark for using the rearranged equation and getting 10.01 and working out ln Kp. You get a mark for working out Kp, and then you get a mark for your units.